So, hello, thank you very much to the organizers for giving me the opportunity to present some of our recent work and some of the not so recent work. Okay, I'm going to talk about using RF radiation for manipulating trapped ions. RF, I'm using it according to the dictionary definition. It's ranging from kilohertz to a few gigahertz. So it includes what we often also call microwave radiation. Let me give a brief outline of what I'll be talking about. I'll remind those of you who do not know yet the scheme that we're using. It's relying on magnetic gradient-induced coupling, which nicely abbreviates as MAGIC. So I will use this expression to, as a shortcut for this scheme that we're using, and then I'll show you how we can actually do quantum gates using this scheme and create entangled states. And then I'll go on to show you some novel ways of doing dynamical decoupling to extend coherence times of single qubit gates, but most importantly of multi-qubit gates. And then I will go on introducing some recent work on quantum simulations using this scheme and the latest developments in our group using two-dimensional ion traps. Okay, so that's the plan, and let's start with the first topic. So why do we want to use this MAGIC? I mean, ion traps have been extremely successful, and some people say it's the gold standard in quantum information science, using laser light to manipulate trapped ions. And we are thinking about scaling up, like Jake said, scaling up ion trap systems. And it turns out that laser light is not only good, it has some technical challenges associated with it. You have to be very careful to keep the frequency of your laser light to a very high stability. For instance, the blood group does this to 1 part in 10 to the minus 10 to the 14, keeping the frequency stable for an electric quadrupole transition. So this is it's challenging for experimentalists. You have to keep the phases stable, intensity stable, and everything. You know about these things. You have to worry about ambient fields, and the usual laser-based scaling schemes involve heavy shuttling, lots of shuttling of ions, so this might be a drawback. Then there are these fundamental problems associated with laser light. That's you have to make an effort to avoid spontaneous scattering. Addressing errors are usually appreciable, and you usually have to cool down close to the motional ground state of your trapped ions. Okay, so this is motivation to use microwave radiation instead of laser light, and then most of these problems are solved, or to a good degree solved. Some of them are not solved. For instance, in our scheme, we are sensitive to ambient field fluctuations. There are other schemes which are not necessarily sensitive to this. And the shuttling, we think we have some concepts that we can have a stationary grid of ions and do not have to shuttle ions around to connect different processor regions. Okay, and I'll come to that later on. Okay, so that's the one motivation. We want to use microwave radiation instead of, or radio frequency radiation instead of lasers. And the other motivation for this MAGIC stuff is that we have this long-range spin-spin coupling in a string of ions. And so what we do is we have our trapped ion string. We apply a magnetic field gradient, a static magnetic field gradient. This gives us two things. We can individually address the ions in frequency space because they all have now different resonance frequencies. And the second thing this magnetic gradient does, it induces this spin-spin coupling here. And this is very useful to do multi-qubit quantum gates or quantum simulations. as I will show you during the course of this talk. Okay, just let me take one slide to remind you how this spin-spin coupling works actually. So here we have a harmonic oscillator potential. We have a trapped ion sitting at position 1, and in this field gradient the spin of this trapped ion experiences a force, let's say that points in this direction. Then we have a second ion sitting here at this position. Now we flip the spin of the first ion, and it experiences a force in the other direction, and it pushes away the second ion also into a different position, and the second ion changes its energy by a certain amount here, and this gives rise to the spin-spin coupling. So we push the second ion by flipping the spin of the first ion, and this displacement, if you just do a classical calculation, this displacement is simply in this harmonic oscillator potential, simply given by this expression here. So this is the force, mass, and trap frequency. And then you want to estimate the coupling constant. So this is the shift in energy of the second qubit depending on the state of the first qubit. And so the energy is just the force that you apply times the distance, and then you plug in the numbers and you get this expression here. And if you have a magnetic gradient, it turns out the force is proportional to the gradient. So this is the field the strength of the gradient, and this is the trap frequency. So you can adjust your magnetic gradient-induced coupling by changing the field gradient and or change the trapping potential. So those are the handles that you have as an experimentalist to adjust the spin-spin coupling. Okay, there are other schemes using radio frequency, quantum logic. I'm sure we'll hear more about the oscillating gradient scheme that has been successfully implemented in Boulder and is being implemented in Oxford. Then there has been a penning trap scheme has been proposed where you get exactly this type of spin-spin coupling, and experiments are underway in Mainz, in Sussex, and elsewhere on making surface traps and using this spin-spin coupling, magnetic gradient induced. Okay, this was the introductory part. Now I'll come to the second part and show you how we do quantum gates using the spin-spin coupling. So our favorite guinea pig, our favorite ion is ytterbium, and we use 2 hyperfine states of the ground state as a qubit and do state selective detection as usual in ion traps using laser fields and for at 369 nanometer. So this here we don't scatter light in this state. In this state we scatter light. That's how we do state selective detection. The experiments I'm going to show you now are done in a typical Innsbruck style trap, but with this additional magnetic field gradient, which is done by using magnets, permanent magnets, as end caps of the trap. Okay, and here you see the so-called parity signal that you get when we do a C0 gate using this sigma Z coupling in a 3-ion chain, and we create this triplet state here where the outer 2 ions are entangled in this Bell state. The middle ion just factorizes out, and then we measure correlations between, as is often done in ion traps, between the 2 ions. So this is probability, or rather relative frequency, to find one ion in 0, the other in 0, and so on. And this gives you this parity signal. And then you vary the phase in a Ramsey type experiment, and you get these typical fringes here that show you that if the fidelity of your state, which is given by this expression here, A is the amplitude of the signal. If the fidelity is larger than 0.5, then you actually do have non-classical correlations. You have a entangled state. Okay, so this in a 3-ion chain, and just note that it's not neighboring ions. It's actually this long-range spin-spin coupling. In a 3-ion chain, it's not so long-range, but it's connecting the endpoints in any case. Okay, and the whole experiment was actually done using a thermally excited ion string. So this is an important feature because, yes, the spin-spin coupling should not be very sensitive to thermal excitation. Okay, and we did this experiment for non-neighboring ions with a fidelity of 57%, which tells us that we have an entangled state, but of course there's lots of room to improve these results. The fidelity here for neighboring ions, the fidelity is a bit better, but still lots of room for improvement, of course. Okay, but the principle has been shown, and the second advantage of this gradient, the static gradient, is that you can talk to each ion in frequency space and with a very small spurious excitation of neighboring ions. So this is a RF optical double resonance spectrum showing the excitation of this ion, or this ion. And meanwhile, we have excitation probabilities in a quantum register of 8 qubits below 10 to the minus 5. So this works quite well. Okay, and then the last thing in this part of the talk I want to show you is how you can adjust the J coupling here by varying one of these parameters. So this is the field gradient, this is the trap frequency. So this is now measuring the J coupling in a harmonic trap using 2 ions as a function of the trapping frequency. Can you see something when I'm here? Sorry. I'm not sure where I should stand. Okay, so in any case, so this is the calculated dependence, just this 1 over nu squared, and these are the calculated measured points. Well, just what I want to emphasize, you can change the J coupling by changing the trapping frequency. That's going to be important for the next things I'm going to show you. Okay, so now let's come to the third part that is not immediately related to what it is immediately related, but it's also a topic in itself. Robust dynamical decoupling. So what is dynamical decoupling about? I mean, what many people, not only ion trap people, but probably everybody who is in quantum information science experiences is that you have a limited coherence time that you would like to extend. And so this is a typical Ramsey experiment from our lab, where we do see the decay of the Ramsey fringes on a sub-millisecond timescale in this particular case. And this is due to magnetic field fluctuations of our qubit levels. And then we also see resonance drifts. So this is over the course of a day doing experiments, we see this distribution of resonance drifts of our qubits. So that's what we want to fight, these two things, and they are rather general, not restricted to trapped ions only. So there have been beautiful experiments systematically investigating this pulse dynamical decoupling, where you use pulse sequences to fight this decoherence. So this could be viewed as an extension of a Hahn spin echo, where you just use many pulses, and then by varying the distance between them and phases, you can achieve very nice results. So here in this particular experiment, the quantum memory has been stabilized using this pulse dynamical decoupling, or in this experiment, so-called CPMG sequences, which is sequences of pi pulses with a certain timing, have been used to extend the coherence time of a quantum memory in a calcium ion. And you see the more pulses you invest, the better your coherence time gets. So this is basically the coherence time. Okay, so these are quantum memories, but actually what we wanted to do is in the spirit of this experiment, which I believe was the first experiment where dynamical decoupling has been applied to a quantum gate, not to a memory. This is actually an NV center in diamond. So you have a nuclear spin and an electron spin, and they couple. This is the useful coupling that you want, and this is the not useful coupling, the environment disturbing your coherence. And the usual dynamical decoupling, if you apply this to your electron spin, it will just get rid of all the couplings. But that's clearly not what you want. You want to keep the good coupling to the nuclear spin, but you want to get rid of the environment. And that's what has been achieved in this experiment here. And so in our experiment, the situation is a little different. Here you have one stable qubit and one unstable qubit. In our case, we only have unstable qubits. So this is the situation that we're facing. We have our two qubits, they are coupled, so that's the good thing, but they are also coupled to the environment, that's the bad thing. And we want to get rid of the environmental coupling, but we want to keep this coupling. And this can be achieved by, by using pulse sequences applied to both ions simultaneously. So the typical experiment we do, we have a Ramsey experiment, so those are two Ramsey pulses here. And then we have our dynamical decoupling pulses, and now we apply them to both ions simultaneously, and you can show, if you do this right, then actually only what remains is the coupling, and the environment is going out. And so we record Ramsey fringes now using either uncoupled qubits or have this coupling switched on. And you see that you have a phase shift of these Ramsey fringes. So you do a Ramsey experiment on one ion, and depending on the state of the other ion, you get a phase shift in your Ramsey fringe. And that's what you see here. So this relative phase shift here. So it means this works, the method works, but the but comes now. This is a small phase shift. If we want to do a C0 gate, we want to have a pi phase shift, not just this little bit here. So, and from usual dynamical decoupling, the recipe would be just increase the number of pulses you're using. This increases the coherence time of your quantum memory. So that's what we did here also, but it was a bit disappointing. So this is now the precession, the conditional precession of one ion depending on the state of the other ion as a function of the number of decoupling pulses. So if we increase the number of pulses, we get to zero coupling. So the reason is pulse imperfections also wipe out the useful coupling. So this is not good. Okay, then we tried different sequences, so-called isotropic sequences, where you change the phase of your pulses. So this is indicated here. So a so-called CPMG XY sequence, where you alternately apply, have pulses with phases along the X or Y direction. Or there's this sequence with a different timing, which has severe consequences, the slight difference here. And then, in fact, it turns out you do achieve, even for a large number of pulses, you still have this conditional phase shift that you want. But the problem is, for a large number of pulses, that is true, but if you go to even longer sequences, in order to have longer coherence times, this drops down rather dramatically. So it's not useful beyond a certain point. And then the final solution that we came up with, was a so-called concatenated CPMG sequence, where you use the CPMG timing, but you use this concatenation and alternating phases. Well, I can't go into the details of this. I'll just show you the result. So this works very well. Even for a large number of pulses, you get this very long coherence time. And this enables us to do quantum gates even with distant ions now. Okay, and of course the next challenge is to have 3 ions or 4 ions or something. Actually, yeah, we have already shown that you can shut down, so to say, all the undesired couplings and keep the desired ones. So if you want to do a C0 gate here or here or here, you can turn off the other couplings by using such pulse sequences. But actually, in the long term, that's not really what we want to do. We want to take advantage of these multi-qubit couplings, so we don't want to turn them off. Okay, so just to summarize, these experiments were led by Andres Varron and Christian Pilz, Benedikt Scharfenberger, and Anastasia Gromova were the PhD students doing the experiments. Okay, and now dynamical decoupling, but a different story. So now we're using continuous wave fields for dynamical decoupling, and the idea is, basically, so far we have we've used this pulse dynamical decoupling, and now we're going to use a continuous wave field. So, so a continuous wave field, you just turn on a coupling field and keep it there. And yeah, there have been proposals, related proposals, as early as in the 50s and by Peter Rabel and other people to that, what I'm going to show you now. And actually we use our ytterbium ion, which has a 4-level ground state, 4 hyperfine levels in the ground state. Then we use 2 microwave fields to dress these states. So we get 4 dress states, and if you plot the energy level scheme of your dress states, then it's something like this. And you can use these 2 states here as a qubit state, which are protected from environmental noise by this energy gap to other states. So dephasing of this qubit would mean that you have to surmount this energy gap, and so the environment has to invest energy to flip the phase, which is why it's getting difficult and to flip the phase, and that keeps this qubit stable for a long time. So here this is a Ramsey experiment, and you see that the Ramsey fringes extend to very long times, starting initially with a coherence time of about 5 milliseconds here. So this works quite well, and you can show that you can also use the scheme to do conditional quantum gates. But I'm not going to go into this any further. Instead, these experiments were done by Ingo Baumgart and Nuala Timoney, and the theory was done by Alex Retzker and Martin Plenio for these dressed state things. Okay, and now I'll come to some very recent things that we did using this magic, but actually this is work in progress, so I'll just give you a flavor of what's going on here in the direction of quantum simulations and long-distance entanglement. Okay, for this purpose, we use a different ion trap, a microstructured ion trap that was developed together with Ferdinand Schmidt-Kahler. So it's a 3-layer trap. Here you see only one layer. You're looking at the top, but what you do see is all these individual electrodes that allow you to shape the potential for individual ions. And by this, remember, I showed you changing the potential means changing the J coupling. So you can modulate your J coupling by applying potentials here. So this is a very compact thing here. This is a euro cent. I suppose it's about the same size as a US cent. No. So the chip carrier here at the same time acts as a vacuum interface, and we simply put this glass thing on top, and then we shine in detection lasers here along this direction, and the camera looks at this direction. And then we can trap these nice ion strings. Okay, and just to show you now a cut through this 3-dimensional structure. So the outer layers, this layer and this layer, they provide radio frequency fields and DC fields to make the trapping. And the middle layer actually acts as a anti-Helmholtz coil where you send currents through that make a magnetic field gradient at the location of the ions. So a nice thing about this trap is that it has a large contact area to the chip carrier eventually. So simulations show that we should be able to run very high currents through this and make very large gradients here. That's the simulations, but then you go to the lab and you realize you've done everything very carefully, but on the chip carrier there's somewhere some stupid 1 ohm resistance which screws things up completely. So currently we are limited to small currents and rather small magnetic field gradients. So the next step will be to fix the carrier to milli-ohm resistances, and then we can apply these really large currents. Okay, so just to show you to show you that the trap in principle works. So these are the segmented electrodes here. And now we trap ions in some place here at the electrode pair here. And then we move the ions to a neighboring electrode pair and detect them. So this moving around works very nicely, and applying these potentials, that's now, we figured out how to do this properly. And here's another little movie where we separate ions. So this is a string of 4 ions, then we pull them apart and bring them back together and pull them apart again. So this all works very nicely. And yeah, so I'll show you in the next part the future, what we want to do using this trap.
Christoph, what's the spacing in that picture?
The spacing is about 10 micrometers. So it's very small compared to the electrode spacing. So this is actually, thank you for pointing out this. This is an interesting feature. So the electrode spacing is 250 microns here. And you can, by properly applying these potentials, you can still deterministically split a chain like this. Okay, yeah, so this experiment is mostly done by Michael Johanning and PhD students Delia Kaufmann, Peter Kaufmann, Tim Kloger, Thomas Kollert. Okay, and now let me show you what we want to do, hopefully in the near future, using this trap where we can adjust the potentials. So I don't know if you came across the notion of the so-called long-distance entanglement. So this is something, you just have a spin chain, and this spin chain has some bulk coupling. So all the spins in the bulk are coupled by some parameter nu, and then you have some weakly coupled spins at the end of the chain. And now the idea is to use this as a quantum bus to entangle the end spins of a long chain. And actually, intuitively, this is rather clear how this works if you remember that there's this entanglement monogamy. So if you have A and B entangled, maximally entangled, it cannot be entangled with C at the same time with a third particle. So here in this case, this bulk, this strongly coupled bulk, is our qubit C, so to say. And they are strongly entangled, have strong correlations. So there's nothing left for A to be entangled with this, and nothing left for B to be entangled with the bulk. So A and B are going to be strongly correlated. So it's at first sight a bit maybe counterintuitive because they are very weakly coupled, but still you can achieve almost maximally entangled states. Okay, so that's what we want to do. But in order to do this, you need some more interesting, for theorists tell us this, more interesting Hamiltonians than just the sigma z coupling. So this type of long-distance entanglement, you can show that it arises in these types of Hamiltonians here. And you remember our spin chain only has sigma z coupling, so we need to do something to achieve such couplings here. And this is a three-step process that I'm going to show you how we're going to achieve this long-distance entanglement, this quantum simulation of a, basically it's achieving the ground state of a non-trivial Hamiltonian like this with non-commuting components. So first we need these weakly coupled end spins. In our scheme, the end spins are most strongly coupled. So this is, we have to do something about this. Then we need to engineer the Hamiltonian to get interactions along Z and along other axes, and then we prepare the ground state of some non-trivial, interesting Hamiltonian by adiabatic variation. So just to remind you, if we have just one global trap potential, we get a coupling matrix typically like this. So this is for 10 ions here. And you see the end ions 1 and 2, they are strongly coupled. 9 and 10, they are strongly coupled. And then you... But using these individual electrodes here, you can actually make all kinds of interesting coupling patterns. For instance, you can have only nearest neighbor coupling between 1 and 2, 3 and 4, and so on. And this has been shown to be useful for making cluster states, for instance, in this paper here. But now I'm going to show you something else. So this is now using this trap. We can make such potentials here and shape the coupling between these trapped ions. So that's a string of, an example for a string of 6 trapped ions. And here you see the coupling matrix, and you notice that these endpoints are very weakly coupled. So this is rather intuitive, I think. I mean, they sit in these potential wells here. So they are weakly coupled, and then in the middle you have this bulk, which is strongly coupled. Okay, so this is the first step, adjust this coupling. Then the second step is to introduce other, not only sigma z couplings. So this can be done by simply, if you have a single, think of a single spin, you simply apply a pi over 2 pulse, 2 pi over 2 pulses, and then this gives you an effective sigma x operator, and that's exactly what we plan to do here. So we have our Ising coupling along the z direction, and then we apply pulses to each of the ions, pi/2 pulses, and then we get this Ising coupling along the x direction. Okay, and then you can, we have this, but now we want to have z and x simultaneously. So what we are, so this is the Hamiltonian that we're really interested in. So having x and z, for example, this is one example, simultaneously, and this can be achieved by the so-called trotterization. So we have small time evolution steps, tau over n. So the total time evolution is split into n steps where we apply either sigma z or sigma x coupling, and then do this n times. Okay, so this is, and now the final step, so we have the coupling constants, we have more interesting coupling patterns, Hamiltonians, and the final step is now to do this adiabatic process. So we start with a Hamiltonian that is simple to prepare in our system. So this is simply all spins aligned, a fully polarized state. And we have this parameter h, which is the tuning of our microwave field. And we have this parameter alpha here, which is the amount of XX coupling that we admit. So this is the effective Hamiltonian, and now we start with this simple Hamiltonian, and then we adiabatically move these parameters. H initially is some h0, so that's this Hamiltonian. In the end it's 0, this h, so this part disappears completely, and we ramp up this alpha parameter so that at the end we achieve exactly this Hamiltonian here. And if you do it adiabatically, we end up in the ground state, and then we should immediately have this long distance entanglement. And then we would measure the correlations between the end spins. Okay, so now this is the theory part, and now I'm going to show you some simulations using exactly the parameters of the trap I showed you. So it should be reasonably close to the real thing. So here you see the fidelity plotted. So the dashed line is just the total effective dynamics numerically simulated. This is the trotterized dynamics. This is the concurrence, measure of entanglement between the end spins. So you see that this works in theory quite nicely, and this can be, you can speed up things using, you can make it faster and still should achieve rather high entanglement between distant ions. Okay, these calculations, they have been done by Stefano Sipilli and Fabrizio Illuminati at Salerno. Okay, so this is almost the end. And just to show you one experimental feature that we are going to use here, we developed this E-field generator. That's actually a bit inappropriate, this name, so it's not generating E-fields, it's making voltages, and we are translating this into E-fields. So it's basically a multi-channel arbitrary waveform generator that can have very many, I mean up to 100 channels, and you can have arbitrary sequences to apply to your individual trap electrodes and use this for making these interesting Hamiltonians then in the end. So these are just some random examples of what this device does, and we're very confident. We use this for shuttling and everything, so it works nicely. And now we want to use it to shape these coupling constants. And the interesting thing is you don't need any lasers or anything. You simply switch voltages to achieve this coupling. Okay, and now just at the end, how much time? None? Ah, okay. So the latest, according to my thing, it's 38 minutes. But, well. Just to show you a surface trap. So this is a very versatile surface trap where you can, typical surface trap, as most people of you know, this 5-electrode design that has been pioneered by the Boulder group and other groups. What we do is we segment these DC electrodes and send currents through, and then you can have these nice gradients which are switchable and can be adjusted. This is what the trap looks like in the vacuum recipient. This is some crystals trapped, so it works. And this is individual addressing using a magnetic field gradient of 3 ions. So it shows that the principle works, but again, there is in this case, an 8 ohm resistance on the chip carrier, which prevents us from applying.
What's the spacing there? Maybe you said it. What's the spacing?
The spacing is around 12 micrometers here. Sorry for not indicating the scale. Okay, so in any case, that's it. And this is mostly done by Peter Kunert, this experiment, and Michael Johanning. Okay, so that's the end. Thank you very much for your attention.
Time for a few questions. John?
So your first experiment where you had the axial gradient, I think you had 19 Tesla per meter.
Yes.
So in these traps, for instance, the 3-layer trap, what sort of gradient do you hope to get eventually? How does that compare with the 19 Tesla per meter?
Yes.
One's a transverse gradient versus an axial gradient. Are there advantages to one versus the other?
Lots of interesting questions here. Okay, so we planned this trap to have a gradient of 100 Tesla per meter, which would be a factor of 5 increase compared to the other one, which is a factor of 25 increase in the coupling constant. And in addition, you can modulate your current. You do not have to have a static gradient. You can modulate it close to the trap frequency and in this way achieve very large coupling constants. So this should not only be a factor of 25 in the coupling constant, but should go up to hundreds of kilohertz according to calculations. But the chip carrier is limiting us right now, so we are sending at most 10 amps through it, so a factor of 10 less what we initially planned. But hopefully this can be fixed.
Christof, can I ask you, the first experiment you showed, the basic RF coupling between, I guess, 3 ions. So what was the limiting factor in your operations there?
For the fidelity?
Yeah.
Okay, there were limiting factors were magnetic field fluctuations and, embarrassingly, the state selective detection in this experiment. So we had we used a camera which was not very good, and we had low differentiation between dark and bright, and so this was only 80% or so detection efficiency. So this
you showed in the magnetic permanent magnet trap, you showed that the frequency was moving around. Is that mainly due to temperature, or do you know why it's drifting around during the day?
It's I think that's an open question still. So what we thought initially is that it's caused by fluctuations in the voltage at the end cap electrodes, which move the ions around in the field gradient and therefore change the resonance frequency. But we made quite an effort to stabilize this, and we don't think this is the reason anymore. So we're really not sure where it comes from.
Have you measured the temperature coefficient
of the magnets?
Yeah.
I mean, no, we haven't. So this could be a reason. But if it's in steady state, the ion trap operated over a day, why you would assume that it's at a constant temperature. Well, maybe, I don't know, yeah. So this is something we still have to investigate. Yeah.
Anybody else? Okay, let's thank Christof once again.
Thank you.